I want to turn next to inference rules and a proof system within propositional logic, which is laid out in Chapter 7 of the textbook. In looking at this topic, we move away from our focus on the semantic underpinnings of this system that we're creating, and we focus instead on creating syntactic rules. And these rules model logical principles that pertain to actual statements. So looking at a system like this hopefully will improve your efficiency and maybe extend your ability to see logical relationships. Each of our inference rules is expressed as what we call a valid argument form, which we notate in metalinguistic variables. If we replace those variables with actual sentences of our system, then that is referred to as an instance of the form. So I want to begin with probably the most famous of all forms and inference rules. It's called Modus Ponens. We saw an example of this before when we were doing truth tables. A Modus Ponens argument has two premises and a conclusion. And the premises are if P then Q, or P arrow Q, and P, and therefore Q. And we'll sometimes use the abbreviation MP to stand for Modus Ponens. We've looked at an argument of this form before, which we saw was valid. What we mean by saying that this is a valid form is that any instance of the form will be valid. So an instance of the form Modus Ponens is an argument that you obtain by replacing the variables with any sentences you want. When you have a valid form, any instance of the form is valid. So we know that if you replace the P and the Q in Modus Ponens with any sentences whatsoever, that will be a valid argument. So let's look at some instances of Modus Ponens. You can generate an instance by choosing any sentence you want to stand in for the variables. So I could just decide I'm going to replace P with A, I'm going to replace Q with B, and then I get the argument A implies B, A is true, and therefore B is true. We know that's a valid form because it's an instance of Modus Ponens. It would be easy enough to do a truth table for this, but we've already done one. You could probably tell that it's a valid argument just intuitively. But should we deal with more complicated arguments? Remember, I said you can replace P and Q with any sentence of the system whatsoever. It doesn't have to be just simple sentences, A, B, X, whatever. They can be compound sentences as well. So let's come up with an instance where I'm going to let P be A and not B. And then Q is going to be either C or D. So I have an argument that looks like this. I know that this argument is going to be valid because it's Modus Ponens. No truth table necessary. Whereas with our semantic approach, we would have had to do a 16-line truth table to determine if to prove that this thing is valid. So that's kind of handy. But now to really apply this in a more useful way, we need to go in the reverse direction from what we just did. Instead of choosing replacements for P and Q and then constructing this valid argument, we need to be able to look at an argument that we don't know ahead of time is an example of Modus Ponens and then recognize it as such. And the key to doing this is to focus on the main operators and then look for other sentences that match the appropriate parts. For example, in the argument I just gave you, the main operator of the first premise is the horseshoe or arrow. So then we think of Modus Ponens immediately when we think of that because we know in Modus Ponens, the main operator of one of the premises is horseshoe. So then I'm going to say what I need for the other part of a Modus Ponens, if I want Modus Ponens, is I need another premise which asserts the antecedent of this conditional. And when I look at my instance, the antecedent of my conditional is this A and not B statement. So I look for another premise that says A and not B, and I find out, sure enough, there is the match. And that tells me that if I conclude the consequent, C or D, that's going to be a valid argument. And if you like to think in terms of the spatial analogies, like talking about bringing things down, then I suppose you could say you find the antecedent of a conditional, you can bring down the consequent. I find those kind of spatial analogies a little bit off-putting because, you know, as I think I mentioned this when we were talking about learning math before, that you tend to lose sight of the fact that it's reasoning if you do that, or you can. If you just start thinking about it like you bring this thing down, bringing it down, like, then you're gonna push it over here and then spin it around or something. It becomes like some kind of board game that's like the most complicated board game ever, or like some kind of dance that's a ridiculous dance. So I mean, don't lose sight of what it is. It's a piece of reasoning where, if you know that something implies something else, then you have that thing, then you draw the conclusion, right, that the second thing is true. So suppose I give you a few sentences here, and somewhere in my list we'll have two sentences that provide an instance, that constitute an instance of Modus Ponens, and try and find the instance of Modus Ponens. So here are four sentences. Where in this list do we find two sentences that fit Modus Ponens? That is, that would be an instance of the two premises up here of Modus Ponens. And if you focused in on the fact that we've got an arrow or horseshoe on sentence 2, that's good. That's what you need to look for to find an instance of modus ponens, a sentence with arrow as the main operator. The next thing to look for is the antecedent of that conditional, which we have here in sentence 3. Sentence 3 just is the antecedent of sentence 2. So sentences 2 and 3, those are the ones that provide an instance of modus ponens. The next question is, what is the conclusion that is licensed, that modus ponens tells us we can draw and know that it's valid based on 2 and 3? And modus ponens tells us that we can conclude the consequent of the conditional. So that's B and not C. So again, we sort of will bring down, if you want to talk about it that way, B and not C. And we know that that conclusion is a conclusion of a valid argument if we have 1 through 4 as premises. So this is the main idea behind our building up a proof system within this formal language. We're going to write down a conclusion that's based on the premises 1 through 4, and then after allowing a little space, over on the right, we'll write down the rule and name the premises that support our conclusion. So we're going to put down that we got this from lines 2 and 3 and the rule modus ponens. Now try one that's a little more challenging. Suppose these are the 4 sentences that we have to pick from, and we have to find the instance of modus ponens again. Now maybe you are tempted to look at the part of sentence 2 that has an arrow in it where it says B implies C, but unfortunately that would be a mistake. This is not an instance of the first premise of modus ponens. The reason why it's not, you could never replace the variables in the rule, in the modus ponens rule, and end up with line 2. If you replace, no matter what you replace P and the Q with, the main operator in your sentence is going to be an arrow. And the main operator in 2 is not an arrow, it's the wedge. So the long and short of this is that when looking for an instance of modus ponens, the main operator of your sentence has to be the horseshoe or arrow. It can't be any other operator. The rule cannot be used on just part of a line. It can't be used just on the left side of the wedge here. So even though you see B implies C and then you see B in another sentence, that's not usable. And if you think about what the sentences are saying, again, 2 says either B implies C or else D. So B might not imply C. So just because you have B, you cannot draw a conclusion there. So let's look more closely again. You need to find a sentence where the main operator is the arrow or horseshoe. And we find indeed that we have that in the first sentence. The main operator there is the arrow. So all that remains to do is see if we can find the antecedent of that conditional somewhere. The antecedent is this entire sentence starting with the tilde. Okay, that's the left side of the horseshoe statement there. Not either B or C. Now we need to see if we can find that as an independently stated premise. And indeed we find here it is, the 4th sentence that we're given. So we do have an instance of modus ponens. It is 1 and 4. 1 and 4 give us an instance of modus ponens. So that means we can write down that 1 and 4 are premises, and we have a rule modus ponens that tells us we can conclude the consequent of 1, which is not A. So there is our valid argument based on modus ponens. So now the question arises, and I'm sure you're asking yourself, can we do more with these rules? It seems much more efficient than working with the truth tables. And indeed we can, but if we just have the rule modus ponens, well, that doesn't enable us to see all the logical relationships that are out there, does it? For example, we know the following is a valid argument, A or B, and then not A, and then we conclude B. You could do a truth table, but hopefully at this point, it's natural enough for you to see that that's a valid argument. But you can also see there is no way that we could use the rule modus ponens to get to the conclusion from the premises. Our main operator in this in the first premise is wedge, and then the main operator in the second premise is tilde. There's nothing where the operator is the arrow. Doesn't involve conditional statements. So if all we have is the rule modus ponens, then what we've got is an incomplete proof system. That is to say, there are arguments that are valid, but if you just have the rule that we have now, there's no way to use those rules, start with the premises, and end up deriving the conclusion. So this raises the question, and I'm sure you're asking, could we have a complete proof system? Is there such a thing? And indeed, there is. The book presents a complete proof system, a system where every single argument that is valid, at least every argument that can be modeled within our system, it's possible to start with the premises, use the rules of your proof system, and get to the conclusion. So it's really quite a neat thing that exists. And using the other rules of the proof system, the other inference rules, you essentially follow the same procedure that we just showed here with modus Modus Ponens. If you find premises that are instances of the form in the rule, then you can draw the corresponding conclusion. So now I'm not going to take as much time with the remaining rules as I did with Modus Ponens. Hopefully you get the basic idea. But I'll just do another video where I briefly present each of the rules, maybe suggest a way to kind of internalize the rule, and then we'll look at some examples of applying the rules.